All right, so elements are made of atoms, and the atoms are made of protons, electrons, and neutrons. Now, a while ago I made fun of the ancients for thinking that there were only 4 elements, but what I'm telling you is the reality is even simpler than that. The reality is that everything is made of only 3 particles. All of our mass, all of our substance is made of protons, neutrons, and electrons, put together in different ways to make different elements. Okay? The different elements have different numbers of protons and usually also of electrons and neutrons, and that allows them to be bonded together with each other. If all we had were elements, then we'd have 100 or so different things, but the universe has a lot more than 100 or so different substances in it. You have thousands of different substances in every one of your cells. You have more than 100,000 different types of substance that make up you, all made from a very small number of different elements. How are those elements put together? They're bonded to make compounds. So how the elements bond together is what is the basis of chemistry, and it's all about the electrons. The protons are what determine what atoms are which element, but it's the electrons that determine how each element behaves. Chemistry is determined by the number of electrons you have and the number of electrons you might want or might want to get rid of, speaking of you here as an atom. Now, electrons can't just go anywhere. Electrons are orbiting the nucleus, and their orbits are prescribed. Their orbits are certain shapes or certain forms that are called shells. And the atoms like to have their shells full of electrons. So here we have some representatives of different atoms. We include carbon here. Carbon, we said, has atomic number of 6, so it has 6 protons. It will probably have 6-ish neutrons as well. And when it has no charge, when it's not an ion, it will have 6 electrons. 1, 2, 3, 4, 5, 6. Hydrogen has 1 proton, usually doesn't have any neutrons, and it has 1 electron when it has no charge, when it's not an ion. Nitrogen has atomic number of 7, so it has 7 protons. It usually has 7 neutrons as well, but it can have 8 or whatever, be a different isotope. But if it's going to have no charge and not be an ion, then it needs to have 7 electrons. Oxygen has 8 protons and usually 8 neutrons as well, and 8 electrons as long as it's not an ion. But the electrons, which are not in the nucleus but are out orbiting, have to fit into what are called shells. This is kind of like the space that they're allowed to orbit in. The shells are arranged closer to or further away from the nucleus, and there can be lots and lots of shells. These simple small elements that biology are made of are mostly close to the nucleus. The shell that's closest to the nucleus can contain only 2 electrons. In hydrogen, it has 1, and it has a space left in the other shell. Carbon has the inner shell filled because it has more than 2 electrons, but then in the outer shell it has only 4 electrons because it has a total of 6. So 2 in the inner shell, 4 in its outer shell, and that leaves these 4 spaces because the outer shell can hold 8 electrons. Nitrogen has the ability to store only it has a total of 7 electrons, so 2 electrons in the inner shell, 5 in the outer shell, and that leaves 3 spaces. Oxygen has 6 in the outer shell, that leaves 2 spaces. And electrons like, as we said here, to have full shells. They like to be noble. This is the full periodic table. And you don't have to memorize it because you'll be given it on an exam, or you can see it on the wall in your science room. And you can see that carbon has atomic number 6, 6 protons, nitrogen 7, oxygen 8, and so forth. This group of elements here is a special group. It's called the noble gases. What's noble about these is that they have full shells. So the first shell has 2 electrons. Now wait, isn't that the number of protons? Yes, but remember that the number of electrons is going to be the same as the number of protons, unless you have charge. The second shell has 8 electrons in it, and so 1, 2, 3, 4, 5, 6, 7, 8. And you add the first shell and the second shell together, and that gives 10. That means that neon here has its shells full. The third shell also has these 8, so 18 electrons means all your shells are full and you're a happy argon. Then there is 18, you can just count 1, 2, 3, 4, 5, 6, 7, 8, up to 18 electrons available in the next energy level. And that means that krypton here, this is not kryptonite from the planet Krypton, this is the element krypton. And this is another noble gas, full shell. These guys, noble gases, are satisfied. They're happy because their shells are full. All of the other elements want to be like a noble gas. They either have empty spaces that they want to fill. Like fluorine has 1 empty space that if it had an electron could become like neon. Oxygen has 2 empty spaces, just like we just saw. 2 empty spaces in its shell, and then it could become like neon. Nitrogen has 3 empty spaces, carbon 4. If we go over to the other side of the periodic table, these elements could become like a noble gas by giving up an atom. If lithium gave up, not an atom, an electron. If lithium gave up 1 electron, then it would only have 2 electrons. It would be just like helium. If sodium gave up 1, it would have 10 electrons, just like neon, and be happy. So there are 2 different ways to achieve that noble gas electron configuration, to become noble, to have your shells full. One is to trade electrons. So sodium has an extra electron, extra meaning that it's out here in this energy level all by itself, and this can actually hold 8 electrons, so there are 7 spaces, but it wouldn't be very probable for you to fill in 7 spaces. It's easier just to get rid of that electron. Can you get rid of that electron? Sure, it means that you would become a positive ion, because now you'd have fewer electrons than protons, but you could do that. Chlorine has, if we look here, chlorine is just 1 space away, just needs 1 more electron to become like argon, so it will take an electron from sodium. So if we have pure sodium, which is a soft metal, and if we have pure chlorine, which is a gas, and we put them together, they will react. The sodium will give electrons to the chlorine, and we'll get sodium ions that are now positive charge, and chloride ions that are now negative charge. The negative charge and the positive charge will attract each other, and we have something called an ionic bond. Ions, the ion of sodium and the ion of chloride, are attracted to each other, and the reason they became ions was that they traded electrons. There's another way to become noble, though, and that is to share electrons. So hydrogen wants 1 extra electron. If we go back here, hydrogen has 1 electron, and that isn't a full shell, but if it had 1 more electron, it would have a full shell like helium. It would be noble-like. So 1 hydrogen that wants an electron and another hydrogen that wants an electron can share electrons. When they share electrons, then they both have a noble gas-like electron configuration, and they're happy. That sharing is called covalent bonding. Covalent. Valence means the outside electrons, and covalent means to share them. So we have two hydrogen atoms bonded together as a hydrogen molecule. Hydrogen gas is H2, two hydrogen atoms together as a molecule. And we can represent that as two hydrogens bonded together like that, or H2, or we can draw it with the two spheres of the electron clouds overlapping each other because they're sharing, or we can show them as balls with the bond represented as a stick between them. Oxygen, remember, is lacking two electrons to become noble gas-like. So it wants to share two electrons. Another oxygen wants to share two electrons. So two oxygen atoms can share two electrons in each of two different bonds. That's called a double bond because they're sharing two pairs of electrons. Two oxygen atoms together make the oxygen molecule O2, which is oxygen gas, the oxygen that we breathe in from the atmosphere. That can be represented like this if we look at the way it takes up space, or the two balls, this time with two bonds between them. Carbon wanted 4 bonds, or 4 electrons, 1, 2, 3, 4, before it became neon-like. And hydrogen wanted 1. So carbon can share with each of 4 hydrogen atoms, and that arrangement makes a molecule CH4. That's methane, or natural gas. We can represent it with the C and the 4 H's, or showing them in ball and stick model or space representation. This molecule that you're probably already familiar with is water. Oxygen, which wanted 2 electrons, shares electrons with each of 2 hydrogen atoms that each want 1. So we get H2O, we get the molecule water, and we represent it like that. Sort of looks like Mickey Mouse. These molecules are made up of atoms, and they are the particles of the compounds. Compounds are made of more than one element put together. We can have molecular compounds like this, or we can have ionic compounds like salt. This is also a compound because compound means more than one element together. Sodium and chloride together make NaCl. The Na is positively charged, the chloride is negatively charged, and that is salt. That's a compound. Salt is held together by ionic bonds. Molecules are held together by covalent bonds, like in water and methane and these other molecules that you can see here. Molecules can participate in another kind of bond because molecules can have what's called uneven electron density, or be polar. That means that you can tell one end from another. If the Earth were a perfect sphere with no features on it, it wouldn't have a pole. But because it's a rotating sphere and it has features, we can represent its poles, its ends. There's an end that you can differentiate from the rest. Water is an example of a polar molecule because the hydrogens up here are kind of a little bit positively charged because they just have one proton pulling on the electrons. The electrons are pulled a lot more toward the oxygen that has a bunch more protons pulling tightly on them. So this part of the molecule is partially negatively charged. This part of the molecule is partially positive charged. There's a definite pole here, a definite difference. The partial positive charge on one water molecule can attract the partial negative charge on another water molecule. This is a kind of bond called a hydrogen bond. Hydrogen bonds are between partially positive hydrogens and partially negative other atoms, usually oxygen, nitrogen, or fluorine. And hydrogen bonds are important in biology. We'll see some examples later.